everyone. Thank you for joining us again in this series on diverging lenses. Hopefully you're finding this material interesting and helping you out understanding this topic. So previously, again, real quick, we went through an introductory video in the Converging Lens series. Please check it out, where we talked about terminology and convention, sign convention, which applies to both diverging and converging lenses. Then we did a couple of videos on ray tracing and thin lens equation for objects inside and outside the focal point. And we already did a video on, worked out a couple of problems and we verified them. We did the thin lens equation first and we verified them using ray tracing. In this video, we're going to do 3 problems. Again, just exercises. So before we begin, please let us know what you think about this series. Like, subscribe, share, and again, comment. We'd like to hear from you. So let's begin. So we have an object that produces a virtual image 60 centimeters away from it. Again, and we're talking about diverging lens. So again, when we talked about in the previous video, if this is the lens, if this is the object, the image has to be to its right. And they're 16 centimeters apart. Okay? 16 centimeters apart. If the object is 40 centimeters away from the diverging lens. So we know that the object D sub O, so D sub O is 40 centimeters away. Right? And now I know that the separation between them is 16. Right? So this is 16 right here. So how much is this? This is 24. Right? You have to be careful. The I is negative. So basically, we have that DI basically plus, DO plus DI is going to be 16. So DI is DO, 16 minus DO, or 16 minus 40, or negative 24 centimeters. And again, we already know ahead of time that DI is going to be negative. So that's how we write the relation between them. Or you could just look at it and say, oh, okay, here's 16, here's 24. So automatically DI is negative 24. Or if you want to do it mathematically properly, there it is, right there. Okay. So now that we know that DI is negative 24, DO is 40, we need the power. So we should expect F to be less than 0. Okay. And the magnification is not only positive, but also less than 1. Okay. And that's what we're looking for right there. And from the focal length, we can get the power. So let's first get F. So thin lens equation, 1 over F is 1 over DI plus 1 over DO. So the usual technique, 1 over F, DI times DO, DO minus DI. Okay? Plus DI. So flip, F equals DI times DO over DI plus DO. Let's plug them in. DI is negative 24. DO is 40 over DI, which is negative 24, plus 40. So here we have negative 24 times 40 over 16. Well, we can divide by 4 here and get a 4. And right here, get a by 8. Sorry, we can divide by 8. Divide by 8, this will give me a 2. This will give me a 3. And this 2 and the 40 will give me a 20. So I have a negative 60 centimeters, or a negative 60 over 100, which is negative, let's see, I don't want to put it in decimal, so we can divide by 10, so that's 6 over 10, then divide by 2, so negative 3 over 5 meters. So we got the focal length is in meters. So the power, so again, the F was negative 3 over 5 meters. So the power, which is 1 over F, which is 1 over negative 3 over 5. We flip this, put it on top, so it will be negative 5/3. That is the power in diopters. All right. Magnification is negative DI over DO. So that's negative. DI was negative 24. DO is 40. The negatives cancel out. I can easily divide by 4 or by 8. So that would be 3 over 5, or 0.6. Okay. So let's see if the ray tracing will confirm this. So here's my ray tracing. I put each of these is 5, so I put the focal point at 60, and have a 3 centimeter or 3 unit object. And let's see where the image lands. So again, the first ray, parallel to the optical axis, emerges from the lens, divergent beam, appears as if it's coming from the near focal point. Second one, through the center, continues. Third one, appears as if it's going through the focal point, the far focal point, emerges parallel, and they all meet back here. Okay? So the image is at 1, 2, 3, 4, 5, 6, is at 30. Okay. Let's see. 2, 3, 4, 5, 6. These are all 4. I'm sorry. So the image is at 1, 2, 3, 4, 5, 6. It's 24. And then the object is at 40. And then this is at 60. Okay. And the height, so it came out to be perfect what we wanted, 24. Again, if this is at 60, this is at 40, the image came out at 24, which is good. And then the height, this is 3. The magnification was 0.6, a little bit over a half, and it looks like it's a little bit over a half right here. So we're good. All right, so this problem checks out nicely. All right, let's move on to number 2. So 2 centimeter tall object, 12 centimeters from a diverging lens. So DO is 12 centimeters. HO is 2 centimeters. produce a virtual image that's 0.5 centimeters tall. So HI is 0.5 centimeters. Automatically from that, we get the magnification, HI over HO. This could be written as a half centimeter. So the magnification could be written as 1/2 over HO, which is 2. So that's a quarter. So magnification is a quarter. All right. What's the power of the lens? Okay. So we need F. So we need F, obviously. And the image location, D sub I. Both of these are going to be negative. Okay. Both of these are going to be negative. So let's begin. So what do we have here? We know what DO is, and we know what the magnification is, so we can easily get what DI is, right? Because the magnification is a quarter, so the magnification is negative DI over DO. So DI is negative DO times M. Negative DO is 12, M is a quarter, so that's 3. And it should be -3, right? Because it's a virtual image. So we have now DI and we have DO, we can get F. So 1 over F is 1 over DI plus 1 over DO. So 1 over F equals DI times DO over DO plus DI, right? And so F is DO DI over the sum. Now I can plug them in. DO was 12. DI was -3 over 12 plus a -3. So on top, I'll just keep it the way it is. Don't multiply things out. At the bottom, I have a 9. 12 minus 3 is 9. So this cancels that, leaves me with a 3 here. This cancels this, leaves me with a 4 on top. So I have a -4. So this is good. The focal point is negative. Okay. And by the way, right here, when we computed DI, it was to the right of DO, which is great. Again, it's supposed to be negative, and it's always to the right of it, closer to the lens. So this is 3 centimeters from the lens. That's 12 centimeters from the lens. Okay. And now the focal point, the focal length is -4, which is good. So that's -4 centimeters, or -4 over 100 meters, or -1 over 25 meters. So the power is 1 over F, or 1 over -1 over 25, or 25 diopters. Negative. Okay? So let's go ahead and see if, well, the magnification told us it's a quarter, and distance to image is -3 with a 12 distance to object. So here we go. So if each is if each of those is 3 units, so 1, 2, 3. First of all, let's get the focal length. It's 4 to the, this is right here. And then the object is at 12 units. So again, ray parallel diverges as if it's coming from the near focal point. Ray through the center continues. Ray from the tip as if it's going through the other focal point on the other side, comes out parallel. They all meet over here on this side, and this is the image. 3 centimeters away, which is what we showed, and its magnification is a quarter. This is 4 units. This is 1 unit. Okay, so this one checks out perfectly. Right? All right, I'm hoping all this is starting to gel. And let's do the last problem. Okay. So maybe it's a good idea also to maybe like stop the video right now, pause it, try to work the problem out yourself, the thin lens equation, see if you get, you know, whatever you get compared to what I get, and then later draw the diagram and see if you also get what I get. All right. That's a good way of doing some of these. All right. An object 20 centimeters away from its virtual image. So again, we have these two are separated by 20 centimeters and 2 times as large. So the object is 2 times as large. What is the power of the lens? So we need the focal point to get the power, or the focal length. All right. So let's go ahead and see. So we have an image. Let's just draw a little representative picture right here. So here's a diverging lens. And then the distance between them is 20 centimeters. So just like we did for the previous problem, dO plus dI is 20. Okay? Because again, the dI is actually a negative number whenever it's on this side. Okay? So if you're not sure about this, let's just take, again, this to be, oops, let's see, 10. So, and the separation between them is 20. So we know that dO is at 30 centimeters. Right? So again, hypothetical, dO is 20 minus dI. It's 20 minus dI is negative 10 or 30. See? So you just have to, again, we have to look at the problem and think about it in terms of thin lens notation, thin lens sign convention. Okay? And the magnification is going to come out to be positive. So M is negative dI over dO. And if the object, if the object is twice as large as the image, then the magnification is a half, right? Because the magnification tells you how large the image is compared to the object. So if you're not sure, we can put it here. M equals a half, which is negative dI over dO. Okay? So, so now dI is, again, negative dO over 2. Okay? So now we have a relationship between dI and dO, 2 of them, here and there. Let's see if we can put them in and solve for both. And from those, we'll get the focal length. So why don't I take this dI that's here, which equals negative dO over 2, and plug it here. Okay? So again, plug dI into, let's call this, the first equation, equation 1. Right here. So I have dO minus dO over 2 is 20. DO minus DO over 2, again, 2 times DO minus DO. So do 2DO minus DO over 2 equals 20. That means DO over 2 is 20, and DO equals 40 centimeters. I got DO to be 40. So I could use either this equation or this equation to get what DI is. So DI is 20 minus DO, 20 minus 40, which is negative 20 centimeters. Perfect. It's to the right of DO, and it's negative. Or I could use the other one. DI is negative 40 over 2. Let me put it DO over 2. It's just this one right here. Negative 40 over 2, which is negative 20 centimeters. Checks out perfectly. So now that I know DI and I know DO, I can easily get F. So 1 over F is 1 over DI plus 1 over DO. 1 over F DI times DO over DI plus DO. Flip both. This is DI times DO over DI plus DO. And let's plug the numbers in. DI was negative 20 times DO, which is 40, over negative 20 plus 40. So I have F equals, keep it on top as such, and at the bottom, I got a 20. Right? Negative 20 plus 40 leaves me with 20. The 20s cancel out, leave me with a negative, and this is 40 centimeters. So F is negative 40 centimeters. So basically, F and the object sit on top of each other. Okay? And now the power, which is basically negative 40 over 100 meters, negative 1 over 25. Actually, 2 points. Let me see here. Divide these two. So negative 2 over 5 meters. Okay? Because divide this by 2 and this by 2, you have 2 over 5. So the power, which is 1 over F, which is 1 over negative 2/5, which is negative 5/2 diopters. Right? Let's see the right here. So 1, 2, 3, 4, 5, 6, 7, 8. I put the object and the focal point over here at 40 centimeters. And then I took a ray parallel. It diverged as if it's coming from the focal point, the near focal point. A ray that is going through the center continues without diverging, or basically without bending. An array coming in as if it's going to go through the far focal point, hits the lens before it gets there, and goes out parallel. They all meet back, and the image is at the 20 centimeter mark. And what did we say about the magnification? It's 2 times. So this is roughly 1.5. This is 3. Yep. Works all right. I mean, again, this is 3 units. It's 1.5 almost. So we're good. So this is it for exercises and diverging lens. I'm going to do a virtual lab on the website that I showed you earlier. We'll maybe take a couple of these examples and see how we can do them on the lab. And then after that, I'd like to get into mirrors. we have the three types of mirrors. You know, we have concave, convex, and plane mirror. So we'll have short series on each of these. And the lab also allows us to do, the virtual lab allows us to do mirrors as well. So we'll try to basically match with what we do with the lab. All right. So again, guys, thank you very much for taking the time to watch these videos. Again, I really hope they're helpful. Please leave us your comments, your suggestions, your thoughts on how we're doing, and maybe some requests you'd like to see. And again, given time and resources, we would love to help you out as much as we can. Thanks again, and have a good night.